All right, hello everyone. Um, name's Mark Ashenhust, one of your teaching assistants for Circuits 2, and we're working on MOSFETs right now. So I'll be going over just four problems something you might be seeing on the exam, something that would be good to look over, explaining my thought process and how I'll be going through them for all of you. And just my steps and my processes. In addition to that, the notes I've written will be published to you guys once all the video and everything's been done here too. This is live, so anyone can join. If someone joins, they can ask questions. And then feel free to send me an email. You all have my email. My office hours are on Thursdays. From 5 to 6 p.m. in office, Goldwater building, or Zoom online, kind of like how this session is going, which this session today is also completely in person too. You're welcome to join me here in the office. Today, I don't have anyone with me. So we'll begin here with the first MOSFET problem we're going to look at. And I'll just take a moment to draw it. Give you a second, I'll explain what I'm drawing. So we're gonna have 10 volts here up at the top. They'll change whether it's a drain or source depending on if we're doing PMOS, NMOS. I'm defining this out here. Currently, right now, we don't know whether it's PMOS or NMOS because I haven't finished drawing the circuit. So we're gonna have a 10 kilo ohm resistor there. Gonna go down, I'm gonna add a little more. So right here is gonna be our gate voltage, which will go here and then into our MOSFET there. Go down, and then I'll toss our arrow there. So now, I won't say it yet, but now you can think to yourself whether this is a NMOS or a PMOS. While I continue drawing, that's gonna be the first thing we're gonna define together. So, and this is going to be a 10 kilo ohm resistor. Great. So we got this. I never labeled the one up top here. We got a 10 kilo ohm up here as well. So we got this MOSFET circuit kind of drawn here. We can see that this is, in fact, give you a second, which kind is this? PMOS, NMOS. This is an NMOS MOSFET configuration. So we're at MOS, which means this here is going to be defined as our source. Here is going to be our drain. And as we've already defined here, this is our gate. Awesome. So drain, source, and then lastly our gate. So going back, now I'm going to define two things for you. That's going to be our threshold voltage and then our transconductance parameter. Our threshold voltage, which I'll be VTN because we're using a NMOS, 0.6 volts, 600 millivolts, and then our KN is 0.4 milliamps per volt squared. Awesome. The first thing I like to do is just write down. So the two things I wrote there, our threshold and our transconductance parameter, are both things that are given to us. I like to also just write down everything, looking at it, everything we know. So we know the drain resistance is 5 kilo ohm. One other thing we want to pay attention to is we see the source there is tied directly to ground. I would write that down. That's a really good thing to just have written down that you know. We know that VS is 0 volts. So when we're looking, we're like VGS It's actually VGS equals VG, because VGS is voltage at the gate minus voltage at the source. Well, the voltage at the source is 0. So voltage at the gate minus 0 is just voltage at the gate. It's good to know. Might come in handy with some things we want to know later. And we will see that. That is going to be something that'll help us out as we move on. So one thing to help us know what mode of operation we're in is, well, we know we got saturation, and then we also have triode, we have cutoff. Those are going to be the main three. That's what we have. And your formula sheet, we're using NMOS, so you can see what's what to see where we're at. Well, the voltage at the gate would be something really easy to figure out here, which would help us. And so to figure out what mode of operation we're in, we're going to need the voltage at the gate, or we're going to need the voltage drain, because VGS, we need to know if VGS is greater than VT, greater than or less than VT. And we need to know if VDS is greater than or less than VOV. So we're missing voltage at the gate. We're also missing the voltage at the drain. So let's solve for one of the two. I'm going to choose solving for, right now, let's do voltage at the gate. So, and we'll use that for the voltage at the drain. So we know the voltage at the gate is, we're looking at it right here. We actually have something interesting if we're using it in terms of VD here. So we have VD, let's just connect this line going down. We have this line going down here, have a resistor there, and then we go to ground there. We actually have something cool. I'll give you a second to see if you can see it. It's a voltage divider. So we have a voltage divider going from VD here, the top. We have a voltage divider from VD down to the ground we have over here, and it's over this 10K ohm resistor. So VG is actually VD times 10 kilo ohms over 10 kilo ohms plus the other resistor, which is 10 kilo ohms. And then 10 over 20 is 1/2. So our voltage at the gate is actually 1/2 of our voltage at the drain. Very good, very important thing to know. That's going to help us a lot as we move on through this. So now let's choose a mode of operation. So let's focus on saturation. That's usually the one you want to focus on. That's most of what operation works on. Like when you're when operating, you're going to be operating in saturation. So let's choose saturation. So we're in saturation when our voltage from the gate to source is greater than VT, which, remember, in this case is equivalent to the voltage at the gate is greater than VT. And or we know VDS needs to be greater than VOV, which VOV is just VG minus VT. It's minus our threshold. It's actually VGS, but remember that VGS is equal to VG. So from this, we know that VDS, we can split up VDS. So VDS is voltage at the drain minus voltage at the source. We know voltage at the source is 0 volts. We also know what voltage at the drain is in terms of voltage at the gate. Voltage at the drain is actually 2 times voltage at the gate. So VDS equivalently can be written as 2 times voltage at the gate. Similarly, VOV, which we were kind of getting at there, our VOV in terms of VG is actually, it's VGS minus VTN. We know VTN. We know that VS is 0 volts. So what we actually have here is VG minus 0.6 volts, which we could also write in terms of VD, which is 1/2 VD minus 0.6 volts. We're not going to use this one because we're going to keep this in terms of VG, and we're going to keep VDS in terms of VG. That way we can use that to help us solve. We have one less variable we need to solve for. Once we know VG, we can solve for VD. So moving on from there, so now we're going to do something else. We're going to assume that we're in saturation, and then we're going to prove that we are or we aren't. If we are in saturation, our prediction was correct, then we will be fine. We continue, we use our answer, everything's good. If we're incorrect, then we're going to have to change our answer. We're going to have to do something else. We're going to have to do triode equations. We're going to have to do everything in triode. So here, I'll do it in saturation. So we're in saturation. I'm assuming we're in saturation. And we know our NMOS saturation equation. Our NMOS saturation equation is ID equals 1/2 Kn, transconductance parameter, VOV squared. Also, we know almost all of that. The only part of VOV that we don't know is VG. The only part we don't know is VG. So we get, we know that Kn, what's right what we have and what we need. So what do we have? We know that Kn out of this, we know that Kn is 0.4 milliamps per volt squared. And we know that VTN is 0.6 volts. We know VGS, we don't know, but we know VS is 0 volts. So because we know VS is 0 volts, we know VGS is equal to VG. We also know what VG is, though. We know what VG is in terms of VD. So that will help us in the end. So we could either solve for a value or put it in terms of ID. So in this case, we can't really solve for a value there at the end. We can't really get VD, so we have to put, what we need to do is we need to put VGS here in terms of ID. If we put it in terms of ID, then we can solve for ID. Once we know ID, we can just find VD. Once we know VD, we can find VG because we already related VD as being 2 times VG. If we found VG, half of VG is VD. We found that relation between the two. So what we need here is we need to find ID, because once we find ID, look it back up here, ID is going to be the same thing as I2. If we know I2, then we can just do VD equals 10 volts minus I2 times 5 kilo ohms, which is exactly what we're going to do once we figure out what I2 equals or ID equals. So we know VD, as I just said, when looking at the circuit, it's 10 volts minus I2 times that resistance, kilo ohms. Amps times ohms is volts. That lines up, that looks good. So we know that VG is half of that, right? VG is 1/2 of VD. Therefore, VG is 5 volts minus I2 times 2.5 kilo ohms. Now we have a relation between those two, and they're both using the same current. So I2 is not the same thing as ID, right? I2 there is split, right? All the currents, Kirchhoff current law, all the currents in that sum to 0. Whatever's entering a junction must leave. So I2 is also I1 plus ID. I1 is what we're going to be seeing coming out past, right? So we have things going in terms of ID. Well, what is I1? What are we getting? What's that current that we're going to get coming down here? What's this current going to be? Well, we could follow it all the way going to ground from VD, right? So we can follow, we start at VD here, we go through a 10 kilo ohm resistor, remember that. We go through another 10K and then down to ground. So we have VD minus 0 volts. So we go here to here, VD minus 0 volts over the sum of the resistances. So we have VD minus 0 volts over 20 kilo ohms. And that's going to equal I1. So I2 is VD minus 0 volts over 20K plus ID. Great. So now we have I2 in terms of ID, which we can use in this equation up here. We can put this into this equation, and then we can put this equation into this equation to solve for ID. It's a long process, but it all come together. So we know that VD, we already wrote it out, VD is equal to 10 volts minus I2 times 5 kilo ohms. But we know what I2 is now. We know that I2 is equal to, we already wrote it out, I2 is equal to VD over 20K plus ID. Now we can put that into VD. VD equals 10 volts minus VD over 20 kilo ohms plus ID times 5 kilo ohms, which is equal to 10 volts minus VD over 4 kilo ohms. 5 over 20 is 4, plus 5 kilo ohms ID. Awesome. And now we can solve for VD. So I would, you can choose what you want to do. I will just add the VD over 4K over, and we'll end up getting 5 over 4 VD equals 10 volts. And this is, sorry, make sure you bring over this negative over here. You make sure you do that. So we have minus, and that's going to be minus 5 kilo ohms ID. And then we can multiply, we can take that 5/4, we can multiply by 4, divide by 5, and we get VD is going to be equal to 8 volts minus 4 kilo ohms times ID. And then we know that VG is what? VG is 1/2 of VD, which means VG is equal to 4 volts minus 2 kilo ohms times ID. Now let's go back to our saturation equation. We know ID equals 1/2 Kn VOV squared, which is ID equals 1/2 Kn. VOV is actually VG minus VTN squared. We know the reason it's VG and not VGS is because VGS is actually VG in this case, because VS equals 0 volts, so we can cancel that out. And we know VG now in terms of ID, so we can plug everything in here to find ID. ID equals 1/2. Kn we know is 0.4 milliamps per volt squared. We know that VG is 4 volts minus 2 kilo ohms times ID minus VTN is 0.6 volts squared. And now is when we take out some algebra, do some substitution, some multiplication kind of stuff. So I'll do ID, I'll divide this 0.4 by 2, so I'll get 0.2 milliamps per volt squared. I'm going to simplify what's inside the parentheses here. I'm going to simplify this because I have the 4 and then the negative 0.6, so I can actually make this 3.4 volts minus 2 kilo ohms ID. As it goes, that looks good, and don't forget the squared, and now we need to FOIL this out. Don't forget, yeah, you can't just square the 3.4 and square the 2K, right? We need to make sure we FOIL this. A very simple, easy mistake. If you're really stressed out on a test, you might do that because you're not thinking clearly anymore. Your brain's tired, you've been going for a while. So we have 3.4 volts minus 2K ID, and then we'll have 3.4 volts minus 2 K ohm ID. So we go through that, and then we'll multiply by the 0.2, doing all that together. You can do that part on your own, and we'll end up we're going to end up with ID equals 0.8 ID squared minus 4 minus 2.72 ID plus 2.31. Now we want to solve for ID, so we need to subtract ID over onto this side. We end up with 0.8 ID squared minus 3.72 ID plus 2.31. You can use, now what I would do is use like a TI-84 or a calculator. If you're on a TI-84, can tell you what to do. We're an 83. I think this would work on an 83. You want to hit your apps on there. It should be next to like the math key, kind of on the left side. You're going to apps. You want to hit 9, which would be like polynomial solver, and then number 1, which will be polynomial root solver. Do it in second order, real numbers, decimal, like just all that next, and then put in these numbers. Put in 0.8 and then negative 3.72 and then positive 2.31, and then hit your like top right key to solve. And it's going to spit out 2 answers at you. It's going to give you 2 roots. And those 2 roots are going to be ID1. We'll have ID1 and we'll have ID2. I'll write them right here, and then we'll I'll copy them onto the other page as we continue. ID1 for me was 3.9 milliamps, and ID2 for me was 0.74 milliamps. Now we got 2 answers. One of these is going to be wrong. One of these is going to be correct. So we need to figure out which one's wrong. We need to figure out which one's right. To figure out which one's wrong and which one's right, we need to see how it performs. If it shows that we're in cutoff, that's clearly wrong, right? And to be in cutoff, I want you to remember what is cutoff. What would cutoff be? Cutoff is going to be when VGS is less than VT. So if we don't pass that threshold, we're in cutoff. Remember that VGS is actually just VG. So that's what we're solving for. We're going to solve for VG, and we want to make sure that VG is above 0.6. What we need to make sure is VG is greater than VTN. That's what we're going to check with our values of ID1, which is 3.9 milliamps, and ID2, which is 0.74. So we're going to test both of these and see which one is greater than our threshold, and that's the one we want. So which one is greater than our threshold? Let's do that. So VG was equal to 4 volts minus 2 kilo ohms times 3.9 milliamps, which was ID. That's ID. That's the one we're using. Let's look back. That's what we had written right here. 4 volts minus 2 kilo ohms times ID. So that's what I'm using on this page. Doing that, writing all that out, we end up getting negative 3.8 volts. Negative 3.8 is not greater than negative, or not greater than 0.6. It's much less than 0.6, which means this value here is not good. ID1 is not good. So let's go ID2. Let's see what VG is for ID2. VG is going to be 4 volts minus 2 kilo ohms times 0.74 milliamps, which is equal to 2.52 volts, which is a good VG. That works. That sounds good. We're not in cutoff. Great. Now let's see if our guess of saturation was correct, because if it's not correct, then we have to restart. We have to do it in triode, because we just solved it with the saturation equation, which is incorrect. So let's see. Let's make sure that this is in saturation. And the way to do that is we can check VD. We know that VD is 2 times VG, right? VG was half of VD, so let's just multiply this by 2. And we end up getting 5.04 volts. There. Awesome. So we know the source is 0 volts. So to be in saturation, VDS must be greater than VOV, which is actually just VD must be greater than VG minus VTN. Well, VD is double VG, so anything minus VG has to over double to be greater than VD, right? If VD is 2 times VG, VG has to be 2.2 times, VG has to be multiplied or added to over double its size. VD is 5.04, and then VG is something less than 2.52. It's 2.52 minus 0.6. So we are in saturation, which meets what we said. Correct. It meets what we wanted to be in. So therefore, we're all good. We are in saturation. We need to find our last value. We know VD. We know VS is 0 volts. We know that, we know VG is half of VD, which is 2.52. Let's find ID. What's ID? I2, sorry. ID, we know ID. Because we assumed it. We know ID is 0.74. Well, actually, let's write that down. ID equals 0.74 milliamps. And let's go back and let's solve for I2. I2, we wrote the equation for. Well, I2 is it's going to be the sum of I1 plus, where did I write that? I1 plus ID, but we can do VD over 20K, VD over 20K, which is I1, plus ID. So it's going to be VD over 20K plus ID, which is going to be, we know what VD is, we solved it for right over here, it's 5.04 volts over 20 kilo ohms plus 0.74 milliamps, which gives us a final value, I2 is equal to 0.992 milliamps. Good, so we solved for everything we needed to know here. It's a good start, good first solution. Sorry for the yawning for some reason. I keep yawning a lot right now. So let's go to our second question. Like I said, all the notes, everything's going to be posted online, so you'll be able to get all this on your own, see everything yourself. So I'll write the second question. So we're going to go back and forth between two things here. I'm doing 4 questions, each one about a half hour. This one we're going to solve for, we're missing the resistor. We're going to want to solve for the resistor to ensure that we're in a mode, and that mode is going to be saturation. So what value does that resistor need to be to ensure that we're in saturation? So I'll write out our question here, question number 2. The top here is going to be at 10 volts. We have 4 mega ohms. We have our drain resistance. This goes down to our, again, it goes down to our gate. Go over here. This is NMOS again, correct? Gate tied there, and then we have a 1 mega ohm resistor here tied to ground. So right, as I said, we're in our NMOS configuration for this one. So what we want is we're trying to find what RD needs to be in order for us to be in saturation. So that resistance there, well, we're NMOS, so what conditions, just in general, the first thing, so we want to see what does RD need to be for us to be in saturation? Well, the first question I would ask, and the first thing you should ask yourself is, well, what conditions do we need to meet just in general? What conditions do we need to meet to be in saturation? Right, and that's something you'll have that written, that'll be given to you, but it's good to know kind of just off the top of your head, and you'll use it so much. VGS needs to be greater than VT, and then VDS needs to be less, yeah, VT, and then VDS needs to be greater than VOV. So VGS being greater than VOV, just VGS being greater than VT, just ensures that we're not in cutoff. VDS being greater than VOV is saturation, less than VOV is triode. So we're trying to ensure saturation. So we need that VDS. Once again, our source is tied to 0. So in this case, we just need VD to be greater than VG. We need VD to be greater than VG minus VTN. Once again, VTN is going to be 0.6 volts. Kn is the same. Kn is going to be 0.4 milliamps per volt squared. So what do we need? What we need here is we need VG, and then we also need VD. We need to ensure that VD is at a certain voltage. So let's solve for VG. VGS equals VG minus VS. We know what VS is, right? VS is 0 volts. VGS is equal to VG. Well, what does VG equal? This is very similar to what we had VG the last time. We have 10 volts here, we come here, we got VG here, then we come down 1 mega ohm, and then we go down to ground. It's a voltage divider again, and this time it's with 1 mega ohm for the load. So where's that? It's right, VG. So VG is equal to our 10 volts there at the top, and then we have 1 mega ohm over 1 mega ohm plus 4 mega ohms equal to 10 volts, and then we have 1/5, 0.2. So we have 2 volts. VG is equal to 2 volts. That's really good, very helpful to know, because that means in order to be in saturation, VDS must be greater than VOV. So we have VOV is VGS minus VT. We've already concluded that VGS is equal to VG, and we know that VG is equal to 2 volts. So VGS must be greater than VG minus VTN, which means that VD must be greater than 2 volts minus 0.6 volts, which means that VD must be greater than 1.4 volts. This is the most important thing we've solved for right now, because that means we need to control RD to ensure, that VD is greater than 1.4 volts. So we just found the condition we need to ensure that we're in saturation, which is a very important thing for us to have. And that's going to allow us to eventually to solve everything here. So so VD must be greater than 1.4 volts. Well, what's the one thing we don't have here? The one thing we don't have here is VD. So what's running equation out for VD? The one part of VD we're going to be missing is RD, exactly what we're solving for. Very easy to figure out. We have 10 volts up here, and we have RD, and then we have VD. So we have 10 volts, we have the current ID that's coming down here, and then RD. So VD is equal to 10 volts minus ID times RD. Well, the one thing we really don't know is RD. We can solve for ID, right? Because we want to be in saturation, and we're using NMOS. We want to be in saturation, so we'll use the saturation equation for current, which is 1/2 Kn VOV squared. The triode equation is a bit long. It's a lot to remember if you really want to. I bet by the time you're done studying this, you'll remember the saturation equation for an NMOS MOSFET. It gets very easy to say once you do it so much. So I'd say, so we'll keep on here. Well, we know what VOV is, right? VOV is VGS minus VTN. We know that VGS is actually just VG minus VTN. We know that VG, we solved for VG, and we said VG is 2 volts, minus VTN, which is 0.6. Sorry, I should have just wrote that out, 0.6 volts. So we know that this is 1.4 volts. So VOV is 1.4 volts. We know what Kn is. We can solve for ID in saturation. So ID in saturation is 1/2 0.4 milliamps per volt squared. VOV squared, which is going to be 1.4 squared. ID is then equal to 0.392 milliamps. Awesome. We have everything now except for RD, which means we can solve for our answer for what RD needs to be to ensure we're in saturation. So VD must be greater than 1.4 volts. I already said that. But now we know what VD is. VD is 10 volts minus 0.392 milliamps times RD, which must be greater than 1.4 volts. Now, you may not have worked with inequalities in a while. I don't know if you have or not. I'll give you a small refresher. Because sometimes it's easy to forget. The only time the sign is going to switch, because sometimes I'll go for greater than or less than. It's when you multiply or divide by a negative number. If we add a negative or we subtract a negative, it will not change. But if we multiply or divide, it will. So if you have any questions on that as we go through it, like why did it change or why didn't it change, that is the rule. So here I want to get the RD alone, so I'm going to subtract 1.4 from both sides, and I'm going to add this over. So by doing that, I get 10 minus 1.4, which is going to be 8.6 volts. Must be greater than 0.392 milliamps times RD. And then I divide 8.6 by 0.392 milliamps, which I get 8.6 divided by 0.2 is 21. So I get 21.938 kilo ohms RD. So RD, we have RD here. RD must be less than 21.938 kiloohms. So 21.938 kiloohms is what we have here. Correct, making sure. Yep, so RD, so 21.9, let's flip this. So we have RD less than 21.938 kiloohms. So RD cannot be greater than 21.938 kiloohms. RD must be less than 21.938 kiloohms to be in saturation. And there we go. So that is the solution to that one. That one was a little more streamlined. It was a different question, something else to solve for, but the answer was a bit easier to arrive to than it was for the other one that we just did. And so now what I think I'm going to do is jump to I'm going to do another question like the first one, and then I'll end with one that's back on that RD thing. I think the hardest thing that you'll run into, and the hardest thing that we've even done so far, was with that first question. It's usually the algebra. The algebra is going to be the part that tricks you up. The algebra is going to be the part that makes you do some work, makes you pull out your calculator, remember how to use some of that stuff you haven't touched since you took calculus, depending on how long that's been for you. It's been almost 3 years since I was in a calculus course, but using all the stuff in these circuits courses really reinforces that. So there might be a couple things you've forgotten, and that's completely okay. But you practice and you'll get back to using them here. You'll use that stuff here. Circuits, especially lots of electrical engineering stuff ends up using a lot of that math knowledge. I do research for ASU for the ECEE school, energy, electrical engineering, energy engineering school here at ASU. I work in neural networks, fault hardening for neural networks for radiation. And the big thing with that for us is there's a lot of linear algebra in that. So I've really had to pick back up on my linear algebra stuff. But a lot of the upper level math classes and some of the upper level math classes I'm in are only focused on linear algebra. So it comes back, you'll get back to it. But you just got to stay pretty solid on your math skills while you do this stuff. So number 3 is like number 1, but I changed a couple things. The number 1 thing that we'll see that's changed here, well, there's 2 main things we'll see that changed. Number 1 that I would notice here is we're not NMOS anymore. We're actually we're a PMOS configuration. So this is a PMOS MOSFET. It's probably the first thing you want to make sure you look at, first thing you want to make sure you see, because you would hate to run through the whole entire thing and then realize, oh man, I have everything flipped. All my signs are flipped. Oh wow, this isn't. So we see that. Then the next thing is our source is tied to ground, but so is something else now. Our gate's tied to ground. So actually our VG is equal to 0 volts. We don't know what VS is though. Because I also wrote this wrong. VS is -5. That's 5K. This is -5 volts. VS is, we don't know. Because VS isn't taken here. No, VS is taken here at the top. We don't know what VS is after that drop over that 5 kilo ohm resistor. So because we also don't know the current there, we're gonna have to find the current there. You need to know that current there to figure out what VS is. So you can, in this case, when we're solving for it, you can do what we did in the first one is you can assume. We're going to assume, is this in saturation or is this in triode? I usually, like I said, I would assume saturation. Saturation is usually where things run. That's where things happen. That's where everything gets done usually. Circuit design. So we're going to assume saturation. So by assuming saturation, we have our current equation. We need to know ID. Well, ID equation doesn't really change. It's 1/2, and instead of Km, we have Kp, and we have VOV squared. In these equations, what's really going to change is we're going to toss an absolute value, but very nice, we were given the absolute value of VT. So we've already got that set, and we can solve for VOV here. Where VOV is going to be voltage source to gate, not gate to source. We'll do source to gate minus the absolute value of VTP. VTP is given to us, that's still 0.6 volts. It's not going to change. We'll do absolute value of VT is 0.6 volts. We don't know the voltage at the source. We do know the voltage at the gate, right? What's the voltage at the gate? 0 volts. It's tied to ground. So VOV is the voltage at the source minus 0.6 volts. All right, well, what's the voltage at the source? We have our 5. That's not, sorry, this is PMOS, right? What's the voltage at the source? Here's the source. This is VS. This is our source up here. What's the voltage at the source? We have 5 volts. We travel down to VS. So we have 5 volts minus 5 kilo ohms times I2 equals, right? So we have VS equals 5 volts minus I2 times 5 kilo ohms. Oh, great. So now we have VOV in terms of I2. That's good because now we could get I2 in terms of ID. What is I2? I2 and ID are the same. And why is that? We don't have anything here on that gate. Nothing's tied. So the reason why it wasn't the same here is because everything, we were all tied together. We were tied together on this. And that was the same for the one that we got back here. This was all tied together. So they had a different current. However, in our new problem here, this isn't tied together. So the current here is the same. ID, the drain at the gate is the same as the drain at the source. For this, so in assuming saturation, this is actually not I2, this is ID. Cool. So what's VOV? VS minus 0.6. So it's 5 volts minus 0.6 volts, which is 4.4 volts, minus ID times 5 kilo ohms. Great, good, nice solve. Well, we know what KP is and we know what VOV is, so now we can solve for ID if we're in saturation. So 1/2, what's KP? KP was, it's the same, it was given to us in the question, is 0.4 milliamps per volt squared. If you don't have the question with you, don't worry, this was given to us. This isn't something you need to solve for or know beforehand. And then we'll have times VOV squared, which is 4.4 volts minus ID times 5 kilo ohms squared. Very, very cool. So then we get ID equals 0.2 milliamps per volt squared. We're doing the same thing we did that last time, aren't we? This is like almost exactly what we had the last time. And then you're gonna FOIL this out. So I foiled mine a little bit differently than some other solutions or another thing you might see. I did 25 I'll do times 10 to the 6 instead of mega, just so I don't write units. So simplify it, ID squared minus, we have 44 times 10 to the 3 ID, and then plus 19.36. So that's that foiled out. And then I'll multiply by 0.2 milliamps, which is really going to knock everything down here. So we end up getting ID is equal to 5K ID squared minus 8.8 ID plus 0.003872, which I could probably do just 38. And then I'll subtract this ID over, so we end up getting 5.5K ID squared minus 9.8 ID plus 0.0038 equals 0. Once again, pull out your calculator, TI-84, whatever, 83, whatever you're using. Go back here. And then we'll solve for ID. We're going to get two answers again, and we'll have to see which one's right. So, using a calculator, we get ID1 and ID2. ID1 is equal to 0.549 milliamps, and then ID2 is equal to 1.41 milliamps. Nice. Now, what do we have to do? Think for a second. What did we do on the last one? Both of these aren't right. One of them's wrong. One of them's right. We need to see which one's cut off and which one's not. We need to see which one makes sense in terms of the problem, and then we also need to make sure it fits our assumption that we're in saturation. So 0.549 milliamps, we need to see what VS is. Well, VS was equal to, let's check back. VS was equal to, or is equal to, 5 volts minus ID times 5 kilo ohms. So we'll use that here. So we have 5 volts minus ID, 0.549 milliamps times 5 kilo ohms, which this gives us an answer of 2.255 volts, which that looks good to me, right? That VS, that VSG. That looks good to me, but let's check ID2. I mean, why not? I mean, we're reasonably certain that it's going to be ID1. Let's check ID2. 1.41 milliamps times 5 kilo ohms. Put that in your calculator. You're going to get negative 2.05 volts. That's bad, right? We can like look at the equations we have and thinking about it. VSG must be, we need VSG to be greater than the absolute value of VTP. Well, VT is 0.6. So if VSG is negative 2.05, negative 2.5 is clearly less than 0.6. So it needs to be greater than. So that means that this 1.41 milliamps is not correct. So we know what ID is. Equals 0.549 milliamps. So now let's solve. We can solve for VD, VSD. What's VD? We have negative 5. My bad. We have negative 5 volts. We have our resistor here, up here. So we have our negative 5 plus ID times 5K. Which is going to be negative 5 volts plus 0.549 milliamps times 5 kilo ohms, which is equal to Negative 2.25 volts. Looks good. And then we can do our, instead of VDS, we want VSD, which is 2.255. And well, this is 255 as well. Negative 2.25 minus a negative 2.255 volts, which gives us a sum of the two, which is 4.51 volts for our VSD. Now we have our VSD, so let's check. We can use that to check and see if we're in saturation. To be in saturation, our VSD needs to be greater than VOV. VOV was what? We solved, well, we can solve for VOV, which is VS minus 0.6. VS minus 0.6 equals VOV. So VOV equals 2.255. Second, 2.255 minus 0.6 is 1.655. So VSD must be greater than 1.655 volts to be in saturation. VSD is 4.51. 4.51 volts is definitely greater than 1.655 volts, which ensures and confirms that we are in saturation. And we've solved for everything here. We have all our answers. We have everything we need. Everything looks good. Good work. Good job. Nice solution. That one wasn't bad. So cool. We can move on to our last problem, which is going to be another solving one. So this example, the one I'm going to go over here, is one that was already given to you. It's one that you've already seen. But, oh, well, if you're in the course, I'm going to do it the similar way, but I'm going to flip the way it's gone. So first you would solve for what the voltages are, and then see where it takes you or what's happening. What I want to do is I'm going to solve for that RD, like what would that RD be? And then we can solve for values, and you'll see why I want to do it like that in a second. So this will be our fourth question. We have positive 5 volts on the top. Go down, we have a resistor. We don't know what this is. Well, I'm going to start with we don't know what it is. And then VD is here. Go out, we have our MOSFET. Come back. We have 1 milliamp here. And then we have going down to a negative 5 volts. And then to ground. So what does RD have to be in order for us to be in saturation? Well, we know this is NMOS, right? Let's look at it. We can see this is an NMOS configuration, and we're given VTN is equal to 0.8 volts, and KN, transconductance, is 1 milliamp per volt squared. What do we know? Well, if you remember from the last one, this gate tied to ground, right? We have nothing else connected here. The current we have here is going to be the same as the current we have here. So we know the current here is 1 milliamp. So that means the current that we have here is also going to be 1 milliamp. So we know what ID is. We know that ID in this question is 1 milliamp. That was given to us. That's awesome. But that's because this was tied to ground right here. That would change. But for sake of this problem, that's what we have, and that's correct. So we'll continue on with that. So what do we need to know? Well, we want to make sure it's in saturation. So we need to know what VD is, because we need to know VDS must be greater than VOV. We know what VG is, right? So, and I'll show you a little trick we got here. So VD minus V source must be greater than VG minus V source minus VTN. Well, why don't I just add this VS over, and then the VS's will cancel here. So this is VD must be greater than VG minus VTN. Well, that's cool. That really helps us out, because now we don't need to figure out what the source is. We just need to make sure that VD is greater than the voltage at the gate, which is 0 minus VTN. So really, VD needs to be greater than 0.8 volts. Negative 0.8 volts. Sorry, not positive. Negative 0.8 volts. So what do we know? Well, we want to solve for VD, right? So what does VD equal? Look at it. It's up here at the top. So we have a positive 5. We have a resistor down to this. Think for a second. What does VD equal? We have our positive 5 minus the current there, ID, which is 1 milliamp, times RD, which we don't know. Well, that's awesome. Let's plug that in. 5 volts minus 1 milliamp times RD must be greater than negative 0.8 volts. Let's add the 0.8 and then add the 1. So we'll add the 0.8 over, so we'll get 5.8 volts must be greater than 1 milliamp and RD. And then we'll divide by 1 milliamp, and we'll end up getting 5.8 kilo ohms must be greater than RD. So RD must be less than 5.8 kilo ohms to be in saturation. And I'm doing this one on purpose. I'm doing this on the beginning on purpose, because the next question is going to tell us something. And it's going to say, assume that RD is resistance. Because we solved this, we immediately know which operation the MOSFET's going to be in based off what we just did. So the next extension of this question was, let's assume that RD is equal to 4 kilo ohms. And now solve for what is VD VS. Well, if RD is 4 kilo ohms, is that less than 5.8? Yes, it is. So that means, what mode are we in? That means we're in saturation. So RD is now equal to 4K. We're in saturation. Awesome. We already know what ID is. And now we know what RD is. So we can just solve for VD real easy. We have VD is 5 volts minus ID, which is 1 milliamp. And we were told that RD is now 4 kilo ohms. 1 milliamp times 4 kilo ohms is 4 volts. So we have 5 minus 4. So VD is equal to 1 volt when RD is equal to 4 kilo ohms. And then we could do the exact same thing for VS. we have VGS is equal to VOV plus VTN. We know VG minus V source equal to VOV plus VTN. VG is 0. So negative VS is equal to VOV plus VTN, which is 0.8 volts. We know we're in saturation. So what do we need here to solve for VS? We need to know what VOV is. Well, we know everything here except for VS. So let's use our current. ID, we're in saturations, 1/2 NMOS KN VOV squared. We could solve for VOV. ID is equal to 1 milliamp. We have 1/2 KN is 0.4 milliamps per volt squared. And then we have VOV squared. So 0.2 milliamps per volt squared, divide that over, and we'll end up getting VOV is equal to the square root of 1 over 0.5, which is equal to 1.414 volts. Square root of 2. So we know VOV now. So negative VS is equal to 1.414 plus 0.8, which means that VS is equal to negative 2.214 volts. And that is our final solution. So we have VS down there, we have VS here. And then we had our VD up here is 1 volt. And we know ID. ID is 1 milliamp. So the reason I started there. I wanted to find what RD had to be in saturation. And then based off that, when it gives me random values of RD, say RD was 4K, awesome. Well, I know it's in saturation. Say it was 5.76 kilo ohms. I know it's in saturation because it's less than 5.8. So it helped out. So I didn't need to think. I was like, is it in saturation or is it in triode? I knew it was in saturation. That's why I solved for what does RD have to be first. I did that first. So it's a different way to do it, to think about it. So looks like that's it. Those are all the questions I wanted to go through. All the others are the same, but it gives you experience that you can go through them yourself. Please message me, email me. We could set something up if you need any help. I look forward to helping you guys out. I'll have another module to help you guys out here coming out soon about internships and careers, research opportunities and stuff. So look out for that. Great, sounds good. I will talk to you guys soon. Have a great day.